Hey folks, Mr. Ray here with our next lesson on transformations of logarithmic functions. So the previous two lessons we looked at um, exponential functions and what its inverse would look like, and then declared that to be a logarithm function. So in the last lesson we looked at how to go back and forth between the two different forms and also how to evaluate some simple logarithms. Today we're going to look at transformation of log functions. Actually, next lesson we're going to look at some of the laws to help us evaluate some more complex logarithms. For now, we're going to look at the transformations. So this is going to be very helpful when you graph any type of logarithm function, if you have to. So basically, we're starting with the function y equals log base b of x. That would be considered our base log function. And then we're going to apply some different transformations. Now, these are the same transformations as we've applied to all other functions we've done in high school. We've got vertical and horizontal translations, moving it left, right, up, down, stretching, compressing, and reflecting vertically and horizontally. So this is a summary of the parameters, and they have the same values as before. For example, if you want to translate vertically, we use the c parameter. So it's basically the log x, which is our base function, plus c. If c is positive, you're moving up that many. And if c is negative, we're moving down that many. Then we've got the horizontal translation. So I've got the same. We're basically applying that to x before we do the log. So remember, it's written as x minus d. So d itself is positive. You're translating to the right that many units, and if d was negative, you're translating to the left that many units. Okay, and then we have the vertical stretch, compression, reflection. So that goes to the left of the log part of the function. And it's got the same ideas. If a is negative, you're reflecting vertically across the x-axis. If absolute value of a is bigger than 1, then you're stretching vertically by the factor of the absolute value of a. And if it's basically somewhere between 0 and 1, after you take off the negative sign, it's going to be a compression by that factor. Okay, and then the last one, the k value. So again, this is the one that's a little strange. So it's going to be a stretch, horizontal stretch by a factor of 1 over k, absolute value of 1 over k, if the absolute value of k is positive, if it's bigger than 1. Okay, and if the absolute value is between 0 and 1, then it's going to be a compression horizontally, also by that same factor, 1 over k. And if k is negative, it's also a reflection. Okay, so if you put all those together, you get something that looks very familiar. Okay, you've got the a to the left, you've got the k to the left of the x, the d value adding or subtracting to x, and then the c value to the extreme right. So you can locate them very quickly. Now, in terms of the order, it's the same as before. So you're going to strip off the values of a, k, d, and c, and then you apply the compressions and stretches and reflections first, and then at the end you apply the vertical and horizontal translations. Okay, it doesn't really matter step 2 and 3, which you do first. It actually works out the same, but definitely this last step has to be the last step. Okay, all translations are done last. Okay, now, so we're going to look at how to graph some of these. So we're going to do one example in this lesson where I give you this function here and ask you to come up with a sketch, a good quality sketch of what that function looks like. And then we'll actually create an equation from some written instructions or transformation parameters. Okay, so this is the important one here. You'll definitely be tested on this. So we're going to use base points of this function. So remember, if this is our transform function, our base function would be, so you can see it's a base 10, so it's log base 10 of x. So what we want to do is find some base points from that base function and then apply these other transformations that are going on here. Okay, so I guess the first thing we can do is strip off the values. So in this case, a is going to be -2. The k value would be to the left of the x, but it's nothing there. So that's going to be an implied 1 because it's multiplying with the x, not adding. And then the d value, so remember, it's not -4, it's +4 because it's x minus d. And then looking for the c value, there's nothing there, so that's a 0. Okay, so remember the default values for translations is 0. Default value for stretch, compression, reflection is a 1. Okay, so how do we come up with our base points? I don't expect any of you to look at this function and know some good base points, but I do expect you to know that if I wanted to get, I could start off with the function, with the exponential function that this is the inverse of. So that would be the function. So I think of this as the base 10. So the inverse function would be y equals 10 to the power x. So I'm going to start off, and I should have given myself some more room here. I'm going to try to squeeze it in. So I'm not going to start off with the base points that I'm going to use yet. I'm going to start off with, so I'm using base 10, so I'm going to remind myself of that. And I'm going to do some points for y equals 10 to the power x. Okay, I got to use the same base for this as I have in my log function. Otherwise, this would be pointless. So I'm going to start with, x values 2 through +2. And then I apply, if I work with the positive values, so this would be 10 to the power 1, 10 squared, 10 to the 0 would be 1. 10 to the negative 1 would be 1/10, which is same as 0.1. This 10 to the -2 would be 1 over 100, which is 0.01. So that's a nice table, but I can't use those points here because this is a log function. But if you remember, the log function is the inverse of this. So I can flip the x and the y values and get the equivalent log base points. Okay, so this will be my x value. This will be y equals log, should have given myself some more room here. So that's log base 10 of x. Or you could just write log x. I'll put a 10 there just so you remember. Okay, so remember, these two are inverse functions. So if I want points for this function, I just take points that were on its inverse and flip them. So for example, this point here, the -2 is my y value, and the 0.01 is my x. So I can go down here and write all my y values. So this will be my, and this will be 0.1, 1, 10, and 100. So these are points for, I'll just write it up here, log base 10 of x, which is my base function. Okay, now that I have these, I can do my transformations. And remember, hopefully you remember how to do that. If not, I'll remind you. So remember the formulas. Okay, these are the parameters we're going to use. And for the x value, which of these affect the x coordinate? That's going to be the k and the d values. So the k, remember, it's 1 over k times x plus d. And for the y, it's multiplying with the a value, adding the c value. So it's not 1 over a, it's just a. So that'd be ay plus c. So now if I just put these values in here, 1 over k would be 1, so it's just x, and then plus d would be plus 4. And then ay would be negative 2y, and plus c is plus 0, so it's just negative 2y. So now I take these x values here, and I add 4 to them. Okay, so that would be 4.01, 4.1, 5, 104, 14, and then 104. Okay, and if I multiply each of these by negative 2, I get 4, 2, 0, negative 2, negative 4. Okay. Now, the other really important thing before we do our sketch is there's always going to be some kind of asymptote. So remember, this is the exponential equation. So remember, this exponential equation would have a horizontal asymptote at y equals 0. Okay, and then when I do the inverse function, remember it changes from horizontal asymptote to a vertical asymptote, and it changes, we just switch the y value here to x, so it's just x equals 0. So this is the y-axis. So the vertical asymptote is the y-axis. Now what happens to it here? Okay, well, the only thing that's going to, if you think of a graph, the only thing that's going to affect that vertical asymptote is a translation left to right. Okay, because if I multiply that, it doesn't change. If I do anything vertically, it doesn't change. So whatever the value of d is, how much it translates. So d is 4. So the new vertical asymptote is x equals 4, because it's x equals d. Whatever the value of d is the horizontal translation. Okay, so I'm going to do my sketch here. Obviously, I don't have a lot of room to work. First thing I'm going to do is look at my points to determine, maybe I could trim the graph down a bit so it looks a little nicer. So you can see all my x values, they're basically starting at 4 and going higher and higher. So in terms of my x, I don't need any negative values for x. For y, I do need negative and positive. So I'm going to start here with my y-axis, and my x-axis will be down the middle. Okay. Now remember, for this scale, I'm going to have a vertical asymptote x equals 4. So I'm going to maybe do scale like this. So this would be 2, 4, 8, 10, 12, 14. Okay, and then for this scale, for the x scale, so I've already done the x scale. For this, I just need to go up to 4 and down to negative 4. So this scale can be a little wider. So that would be 4. This would be negative 4. And now I just put my points in. Before I do that, I'd always like to put in my vertical asymptote, because that gives me a good reference for, where the points should be. So x equals 4. I'm going to draw that in as a dotted line. Okay, so all my points will either be on this side or this side, and I can tell from the x values they're going to be on this side. Okay, so my first point is 4.01, so just to the right of this, and 4, so something like this. And then 4.1, which is a little bit more, but that's down to 2. This would be 2 here. And then 5, 0. So remember, that's 4. Oh, I got my scale wrong here. Okay. 6, 8, 12. Okay, so it's 5, 0. So 5, 0 would be right here. Then 14, negative 2. Well, 14 is, well, it's going to be out to here. Should have made my scale a little bit longer so I could fit that point on. So it's 12 and then 14. And that's negative 2. Okay, so you can see I'm going to have a curved, like this really takes off this way. So I can start here with my arrow and then curves up here like that. Okay, so this would be the graph of g of x. Okay, so hopefully that makes sense. The big change for base point transformations for log functions is you have to start with the related exponential function. It's a lot easier to get these points and then flip the x and y values. That becomes your log base points, and then you just transform them like we normally would with the a, k, d, and c values. Okay. Also remember, put in your vertical asymptote. It's a very good way to understand where your points are going to be, okay, and make sure that you didn't make any mistakes. Okay, so that's graphing. Hopefully you get the gist of that. This one, we're going to look at some written characteristics of the transformations. We're going to strip out the a, k, d, and c values, and then we're going to put them into our equation. Logarithmic function f of x equals log base 10 of x has been vertically compressed by a factor of 2/3. So vertically compressed, that's the a value. So I'm going to say a equals 2/3. Now, it's possible that it might be negative 2/3 if it's also vertically reflected, but they haven't told us that yet, so I'm just leaving it as that. Okay, horizontally stretched by a factor of 4. So remember, horizontally the factor is 1 over k. So I'm going to write the factor is 1 over k is equal to 4. So that tells me that k is equal to 1/4. Okay, and then reflected in the y-axis. So if you think y-axis, if I reflect in the y-axis, I'm reflecting horizontally. So that would affect the k value. So I then say that this is reflected. So what happens to k? It becomes negative. So the number part stays the same, but it's negative. Okay, where were we? It has also been horizontally translated so that the vertical asymptote is x equals negative 2. So you could write down, say, vertical asymptote is x equals negative 2. Okay, remember from the last example, whatever the vertical asymptote is, that's your d value. Last time we went the opposite way. Now we know that, well, if that's the vertical asymptote, that means that d is equal to negative 2. Okay, and then vertically translated down 3 units. So that's the value of c, very straightforward. So we've got everything we need. We know that there's our base function. So our transform function, I'm going to call g of x. Okay, that's going to be a. So a, the value of a was 2/3. And don't change that to a decimal because you'd have to round or chop digits off, and I don't want you to do that. So, and then we have our log. So this log function was base 10. So you don't have to put the 10 there, but there's nothing wrong if you do. And then in some square brackets, this is where I put my k. K is 1/4 bracket x. And then it's going to be minus d. So it's minus negative 2, which is plus 2, round bracket, square bracket, and then plus c. Did I get that right? Oh, it's down. Yeah. So that c would be 3 if it's translated 3 units up. This was translated 3 units down, so that's negative 3. So that would be a minus 3. Okay, so that would be your transform function based on these instructions. Okay, and if we wanted to, we could go back and graph this, knowing all these parameters and knowing the technique that we learned in the example 1. Okay, so hopefully you get the idea of how to graph and how you create equations based on transformations. So we've got some practice questions for you here. Give them a try. Hopefully it makes sense. Okay, and our next lesson, we definitely will be doing looking at the different laws of logarithms, logarithm laws. Okay, so we'll see you then.